Okay, we're pushing live to YouTube. I'm checking the audio and the video now, just so everyone's aware.
Thank you.
You sent the wrong message. Supposed to Karen.
Oh, sorry.
Yeah, I sent a message supposed to you, but
Oh.
actually to everyone.
Yeah, Longwood Towers, yeah.
No, yeah, sorry.
Does Alfredo have any slides? Should we try to get those up?
Yeah, well, I'm gonna share my screen.
Oh, okay, great.
You wanna try?
Yeah.
Can you see my screen?
Yes.
Yes.
Good. All right, I mean, we can leave it there.
Okay.
Okay.
We'll have just wait 2 more minutes. We can start. So it is the MIT Media Lab is part of which school the Media Lab is part of? Is it
Department of Architecture.
Oh, okay.
Yeah, well, it's kind of independent, right? Yeah, the Media Lab research in terms of like the research they do. It's interdisciplinary. It's like the intersection between design and technology, and a lot of like social component.
I see. Yeah.
Yeah.
Sorry to interrupt. I'm just going to hit the recording button, just so you guys know.
Okay, great.
Thank you.
So how many people we have? 21?
Yeah, but should we wait?
Yeah, we usually have more than these numbers.
Yeah, but should we wait till a minute or two after the start time, just so people have a chance to?
What we usually have like 60-70% attend
Yeah.
this meeting. Maybe we can. If you don't mind, we can wait 2 more minutes.
Hi, this is George with Productions. I just want to interject a minute. So we are pushing to YouTube fine. That's coming up fine, but I'm double checking that it seems to be a problem with the actual Speaker Series website. It doesn't seem to be receiving the video, but it is going through YouTube. So if you just want to make a quick announcement for any reason that if they are having problems, that they should refresh their browsers. And that should help kick it up.
So they can use YouTube, but not from the speaker website.
It should be up momentarily, but if not, the best option would be to go to the actual YouTube site.
Okay.
Just in case, as a backup.
Okay. Yeah, I think it is about the time. Let's maybe some student will join in later. But today's number is to be lower than usual number. Let's just wait 2 minutes. I will just start in 17th.
Sounds good.
Thank you.
George, would you be able to pass me a roll?
Just a moment, I'll do that now.
Thank you.
Hi, Alfredo. Such a great to see you.
Hi, Elena. Nice to see you too.
Thank you for joining. It will be really fun.
Thank you for the invitation. How's everything in Boston? Good?
Sunshine. It's actually quite nice. So good to see a sunny sky. How's everything in your corner?
I'm in Florida now. Everything is good here. Yeah. Sunny and warm.
Good. Hope you will come.
Yeah, I hope so too.
Yeah.
When things come back a little more normal.
It will be in the spring.
Yeah, well, hopefully.
In April, everything will be great.
Yeah, we need to make it up for this year. Too much time in the house.
I think we can start. We have 46 people here. Some students, some faculties. Some will join in a little bit later. So before I introduce our speaker today, I just try to emphasize that you are encouraged to ask questions at the end of the talk, and also after the talk, you will chance to talk with Dr. Morales to ask questions. And so you can either raise the hand using the chat box, or you can just type your question through the chat box. And one thing, just remind you, the IT person just told me the live stream on YouTube should be fine, but momentarily in the speaker service website may not be that well. So you need to refresh the browser. So if you have any troubles, just maybe just using YouTube for today. Okay, so for our speaker, Dr. Morales, is that right pronunciation? Sorry for
yeah,
okay, great. So he worked in the MIT Media Lab, and also the principal research. Hold on a second, the principal research scientist at Rhizome Production System, and as he also worked in other institute before, and so he has worked closely with many researchers from academia and also industry. And his work is trying to understand the complex social behavior by analyzing big data using complex algorithms such as network analysis, artificial intelligence approach. So today he will talk about the modeling complex social networks at multiple scales. So without further delay, I will give the podium to Dr. Morales.
Thank you very much, Gentile. Thank you very much for the invitation, Elena and everyone. It's a real pleasure to be here and to discuss with you the work that we've been doing. And okay, let me put this here. So, okay, do you see the video? Yeah?
Yes.
So I like to start all my talks with this video because it's the best example of what a complex system is. These are birds, they are flying, and by the way they are like interacting with one another, keeping each other like close enough and far enough to stay like in this limit, they create these new things in large scale, this blob that emerges, right? This is a structure that emerges from their interaction. And it's not something that happens by chance, it's not something that happens by random. And there is a feedback between the behavior that these individual birds have with the structure that they create in the microscopic scale. There's a feedback between how that affects their purpose, like surviving, or like which is pretty much the main purpose of every living thing. But you know, like their purpose of surviving, of like being safer, of I don't know, like distracting the predators and so on. And that's complexity. It's structures that arise from interactions because those structures in some way, in many kind of systems, like there's every type of system, but feedback into the functioning and the purpose of the individuals. If we, one second, look at the world nowadays, well, we also see other types of swarming behavior, but we also see structure and we see large scale dynamics and interactions and things arising and emerging. This is the network of Twitter communication. The lines here are tweets, but if you think of the airplane network or many other types of social networks, you will find you know, like similar structures. And this is important to understand because the world is becoming every time more complex, and at the basis of all of this are the interactions that are happening either in the large scale, like the whole world, or or even within companies, and this is like, for instance, like communication within firms. So you have here like employees sharing information and working pretty much. So you have social networks at every scale within firms, within cities, and across multiple geographical lengths. And understanding the structure of this network is crucial and it's critical if we want to design effective interaction and interventions mechanisms. And that's sort of like what I'm going to be talking about. So we as humans are interconnected and create systems, whether embedded in industrial and economic systems or political countries and so on, and are embedded in a planet. And all of these systems have multiple agents and multiple interactions, and all of these combined together creates a lot of complexity. And the let's say an example, and very clear example of what complexity is, you can find it in the diseases, right, and the epidemics. So if you look here, this is the bubonic plague in Europe back in the 1300s, 1400s, a long time ago. And it shows the different colors, the different times in which these infections happened. And you can see that it looks like an expansive wave, right? It has a very clear structure because at the time people would like move from one city to another city by horse and so on. So it shows this regular spatial pattern. given the complexity of the social system by that time. Now we have airplanes, and we have globalization, and we have high-speed trains and so on. And something that sparks in a country like China creates immediate consequences across the whole world, like the case of the coronavirus. And then you have countries like Italy and Iran, and then the United States, and then Brazil, and blah, blah, blah. And it's just an erratic and very complex behavior, very complex because it's heterogeneous, it's unpredictable, it's different, it's not as it used to be before. And just to show you some examples from my colleague Hiroki Sayama, here we have the spread across the whole world. So I'm gonna restart it. So something that started in China immediately across the whole world, spreading and creating spikes of cases that with absolutely no clear or regular pattern, but very irregular. And here you have in the United States. So once the spikes, the red is spikes, and blue means like that it's decreasing. And you can see, like, again, I mean, the behavior is extremely complex. 1 second. All right, and in the background, there is the whole, is because everything is connected, because things, I mean, people and materials are flowing across different regions of the world and within cities and so on. And I'm talking about epidemics and interconnections, but the complexity of human systems, like it's very large, and it's increasing with more world population, with more globalization. There's many challenges that the UN have identified and that we need to work towards. And it's important to understand that the map is not the territory, you know, like complexity. Again, like people make plans, policymakers make plans, and the reality swipes their plans in their faces, because reality is way more complex. There are many interdependencies and events that are like constantly shocking the world, and that are also like just the natural behavior of the world that we're living in, with all the people that we have and with all the communication. So I'd like to show this example. 2020 is the third perfect example of what unforeseen events are like. And we probably need to accept that that's the world that we're living in, and need to rethink our strategies and so on. But first of all, we need to understand what is happening and what's going on in the background of all these seemingly disconnected things, but that are all part of emergent processes of our social system. And the first lesson here is that formal, it's not the same as informal in social systems. So when you have, this is firms, for instance, but you can think of this concept, you can translate it to many other types of social organizations. So in firms, you have people and roles, and people respond to other people, like they have to report back and so on, which would be like the chart on the left. But when you actually see how people are communicating with one another, how they're seeking for advice, how they're seeking for resources, and just like how information is actually being like shared, transferred, and decisions are being made, and you get like a completely different picture of what the formal structure would be like. And this is because something is your ideal of the world and your ideal of society, and another thing is what actually happens. You know, another thing is what actually like it's occurring, which is at the end like the real stuff. You know, so the thing is that as we forget about the informal, which is the actual structure of the social organization, and focus only on formal stuff, we miss information that is crucial for things to function right. So understanding or the whole thing that we are pursuing as a science in social complexity and complex systems is to understand the natural behavior of social systems, such that we can define structure, design better organizations, and make better decisions, and not the type of improvisations that we constantly see and that we have witnessed also with coronavirus. Anyway, but in order to advance in all of this, we need to observe social systems, we need to quantify, we need science, we need data, we need numbers. And sociologists use statistics, and that's good. You have data from surveys, from questionnaires, and so on. But there is a fundamental problem with the statistics, and is that like aggregate views of society, just like in terms of these are like pie charts or bar charts and so on. They aggregate too much the information and they miss patterns, spatial patterns of organization, dynamical patterns of organization, and a bunch of information that it's crucial about like the social system that we are dealing with. So we really need to open up those boxes and not only think in terms of proportions, but also things in terms of dynamics, in terms of like how things are spatially organized, how things are influencing with one another, how those pictures look like. Because with those, that more information will actually take us closer to understanding the territory and not only the map of the system that we have in our heads. And the thing is that in terms of patterns, there is a whole science behind understanding the emergence of patterns and the spontaneous emergence of patterns in social systems, which is complex system. And there are things that we observe, there are certain patterns that we observe that seem universal across different types of system. And it's not that suburbia behave like zebra or like the like the desert or whatever. But the thing is that there are fundamental relationships between the interacting particles in the microscopic level that can be shared across multiple types of systems and create these sort of microscopic patterns of self-organization. And one of these types or models is social networks, networks. So with networks, we can link individuals in a population and observe the structure and measure the structure of that social group. Something that by the naked eye just looks like a bunch of kids united there together in a single room. When you see the network of who's friends with whom, sort of like that informal network of communications, you see that there is a rich structure. There's groups. There are kids that are in the middle of the group. There are kids that are in the periphery, or there's a bridging between the different groups. So all of this is more information for us to design better interventions and better policies as we learn how that system looks like. This is another example. This is the example of friendships in a high school that they did some surveys, and they also asked kids, which are represented here by balls, who's your friend? And the color indicates the ethnicity. Yellow and green represent either white or African American, and the pink represent Asian students. And the clusters are represent gender and class. So you can see that boys are friends with boys, girls are friends with girls. There is a strong segregation of certain ethnicities, but others are more diverse and more mixed. And again, very simple questions, very simple local rules that would be like who's your best friend or who are your 3 best friends. And if you aggregate and you observe the whole thing, you can learn how that system is structured, and then you can design, where to intervene so your actions are more effective. And then and this is good. So we can do this in high schools and so on. But when we're talking about cities, countries, society, companies, large scale, how do we do this? And the answer and the key is in the mobile phone, right? So because we are texting and we are tweeting and we're posting things and sending things, as we do our daily activities, we are leaving behind a huge amount of data that individually shows like your information, and there's a bunch of like privacy and ways of dealing with this data so it doesn't compromise people's identities. But that if you analyze it transversely in the aggregate, just like the census, you get a bunch of information about the social system that produced that data. And with that information, again, you can know better what you're dealing with. So there's patterns. However, these patterns of information they're not in column X and column Y. These are just like unstructured patterns of information that are scattered and throughout the whole data set, and that it takes research and work to analyze and understand in order to extract them. And they go to the core of sociology. So sociology, if you read the actual definition, says to understand the structure, the interaction, the collective behaviors, individual and macro. You know, it's like that link between how people are behaving, why they behave the way they do, and so on. And we are just providing better tools. I mean, new tools. It's just our innovation is in the tools, so we can now like observe this actual process of the aggregation of individual interactions toward macroscopic systems. And in the background, the concept of complex system that I'm talking about here is emergence, which is system properties that arise from the interaction of the parts. It's related with the video that I showed at the beginning. And it's completely related with the collective behavior, whether it's independent, it's dependent, and so on, and all the types of interdependencies. And in order to move a little forward, this is related to the core of sociology. So there was a thing called social physics. I think it was coined by this guy, Durkheim, 1987, in which he was like trying to demonstrate that, you know, certain religions have different types of behavior. So it's one of the first times, or like, I mean, the first or whatever, I don't want to get in trouble with like those technicalities, but one of the first attempts to do social analysis through quantification, by analysis, by surveys, by saying like, yes, there are rules that are like explaining the social behavior. And at the time, the competition, which sort of continues to be, is with sciences like physics and sciences like chemistry, in which the outcome is predictable, in which like things are easier to model using calculus or even statistics. Social behaviors are different. They are way more complex. What works in one context doesn't work in another context. You know, like you poke it here, response there, you think it didn't matter. 3 years later, you notice that it did. And it's just, there's a bunch of complexity in societies, which makes it different from the systems that are generally analyzed by physics or chemistry and all of these things. So because of this inherent qualities of social systems, there was this huge debate in which whether you could predict the behavior of social systems or not. And the answer is complex. You know, it depends which type of predictions you are trying to make, that yes, you can make this type of predictions or not, you cannot make those type of predictions. For instance, I cannot know when the next hurricane will come or when the next market crash will come. If I say that's going to happen on April 21st in 2024, you'll believe that I'm crazy, because like I don't have the power to make that sort of prediction. Even if the best machine learning algorithm, you know what I mean, says that that's when it's going to happen. But I can know, I live in Miami, Florida. I know hurricanes are frequent. I know they come from there. And I can be prepared such that when they happen, I'm not unprepared. And that's also another type of prediction. It just increases the horizon of the event when it's going to occur. And either way provides huge value for strategies and so on. So anyway, there's a lot of discussion there, very cool, at the very basis of what complexity actually provides back to the science of social systems. And as I was saying before, the whole like value of this type of research is to gain information about the structure and the dynamics of the system, understand its nature, because there is something called the Ashby law of requisite variety, which means that systems need to match the complexity of their environments if they don't want to fail. Likewise, interventions and strategies need to match the complexity of the thing that they're going to be dealing with if they don't want to be fragile to unexpected behaviors that they cannot respond to and therefore fail. So in order to have in order to have strategies that can respond adequately to the things that we're going through or whatever, we need to understand the behavior, the natural behavior of that thing. And I say thing, but I'm talking about social systems. Anyway, such that we can move from a simplified view of society in which that's like real data from Venezuela back in 2013, you had like half and half of the population voting from different parties. But when you look at the actual networks of communication, you observe that social network is completely fragmented and polarized. Information is not flowing from one pole to the other pole. It's pretty much as if you have two different and disconnected groups, social groups, coexisting under the same space. And if you look at, this is the network of Congress men and women from the US, and you can see how it's gotten increasingly polarized in terms of the link here represents if they voted for the same issue, like correlations in their voting patterns. And understanding the structure of social networks is important because we need to understand what is happening. And it's things called revealed preferences, and it's like all these politicians can say, yeah, we care about unity and blah, 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 and all these things. But if you observe their behavior, they're revealing their preferences. They're super, super, super polarized. Anyway, so social networks, it's a model, right, to represent interactions among agents, right? So you have agents, you have nodes that can be represented by dots or whatever, and then you have links, which are relationships, interactions, interdependencies. And these links, they can have many meanings. They could be communication, but it could also be dependencies of jobs, who employs whom or who buys what at whose stores, and so on. All the types of interdependencies that you can find in social systems. They can also be geolocated, they could have additional information and so on. And social networks have certain properties that are important to understand if we want to understand social networks and social systems. Anyway, so the first is a small world. I'm going to go through them with some examples on why they're important to understand. High clustering, power law distributions, and nonlinear growth. And the topology matters. So at the beginning, people thought that social networks were like random networks, like I choose randomly who do I talk to or interact with. And that creates one type of topology, the one that you can see there on the left that says random. And what happens is that reality is not like that. It's way more complex. So there's a property called clustering that says that people, if you are my friend and I have two friends, for instance, it's very probable that they have talked to one another or that they know each other because they have a friend in common. So that creates a sort of like modular and it's like connections are not randomly distributed among the different agents, but they are not either concentrated homogeneously like in a random network. Instead, we find something that it's called scale-free distributions or fat-tailed distributions that say that you have a small number of very highly connected users that you can consider what they call the super spreaders, they call it during the pandemic, but it's just like hubs, and it's like related with the Pareto distribution, the 80-20 rule. In this case, it doesn't have to necessarily be 80-20, it can be 90-10 or another number. But the important here is that the distribution is inhomogeneous. And so this creates many types of, many properties in social networks. One of them is the small world property, in which that says that people are, a very famous experiment by Milgram that said that, send this letter to this person from one state to another state without knowing exactly how it's going to get there. But, someone who lives nearby, so you send it to that person and it's hopping until it reaches its final destination. And they found that in average, people are connected by 6 individuals alone. And I think on Facebook, that number is down to like 4 or 3 or something like that, So like society is very, very connected. So in the moment you have an outbreak or something that spreads from individual to individual, it's very easy to achieve a system-wide spread because of this, the complexity of these interconnections. And the hubs have a very a crucial role here. They emerge dynamically, hubs, so nodes that have connections in time tend to have more connections. So like the rich get richer mechanism, this is the Barabasi-Albert model. And these are individuals and very few individuals that can reach in one hub or 2 hubs pretty much the whole or very large portions of the network. So by limiting, for instance, during a spread, by limiting the activity or by limiting the access to super spreaders, it's very few individuals that you can target, but that will decrease dramatically in a non-linear way. That's a whole complexity thing, that individuals will decrease dramatically those rates of contagion. So here you have the two distributions. What would be the power, the normal bell curve and the power law distribution. And well, you know, individuals are more in the social networks, are more in the power law distribution. This is from the book from Barabasi, what a super spreader looks like. So you have one people in one event, you know, like they made all these people sick, but from all of those people, one guy is another popular super spreader that takes it to another place, and then another guy is even more popular, you know. So with 3 or 4 connections, you pretty much reached a huge amount of individuals. And this is one example from the book from Barabasi. This is the sexual encounters, and each link, the dots here represent individuals, male and female, and the links represent a sexual encounter. And you can observe there is a giant component. There is also all these separate components, and there's a whole science behind understanding how components emerge in the first place, how nodes get connected to other nodes, and so on. But anyway, once you applied and to observe these sort of things, you notice there's a power law distribution. There are few individuals that are having, you know, a lot of sexual encounters, and therefore those individuals are the ones that are spreading most of the diseases once it reaches them, because the network, it's something called the vulnerability of the network, which is if you hit one of these hubs, you spread the whole thing. And hubs can also be geographical, so in a larger scale, not in a lower scale. So you can think a lower scale is like in a company, you know, there's a popular guy who talks to everyone, blah, blah, blah. But in a larger scale, when the nodes are aggregated into cities or into geographical regions, then you have population density, economical importance in the world, and you have all the complexity of the planes network and the airports network, in which you are one flight apart, one flight away, depending where you live, from pretty much the whole world. So it's very difficult to contain something that is spreading in this network. So this is part of one of our papers. These are geographical networks of people travels within one country, in Cote d'Ivoire in particular. And the colors of the links represent their modular structures, or pretty much like the geographical patches in which they belong to. And you can see that regardless of being a huge country, you know, like the city down there, the 2 cities down there will gather most of those links and you know, connect with other big cities and so on. And that's like, well, that's the structure of how humans are going from one place to another, and will be the structure of how viruses will travel from one region to another region, just because they travel within humans. And that's when the understanding the structure of social network matters so much when we are doing any type of intervention with social systems. Anyway, this is a video in which you can observe the emergence of these links. We are creating links there after one person makes one phone call from one antenna to another antenna. You can see as it gradually starts to appear, the network of human displacements in Cote d'Ivoire. We also have a video that I'm going to show, it's very short, of the same network, but with phone calls rather than human displacement. So here, every dot is a phone call going from one point to another, and it's 4 a.m. and the country slowly wakes up. And as it wakes up, you can see the information flowing from everywhere to pretty much everywhere, but again, within a network, which there is an interplay, and it's a very nice experiment to observe the relationship between human mobility and human displacements and their communication, because they are indicative of one another. They're not independent. And using one information can infer from the other one. Like, I mean, observing communication can infer, it can teach you of human mobility. Anyway, and you have here, so this is from a paper from +ONE, very cool. They did a commuting network, how people commute. and they find, you know, like again, like cities gathering all these connections and creating these patches where most of the, I mean, these patches, what they show is that these are locations that are densely connected with one another. So when we're thinking of lockdowns and how do we open and what do we open to and so on, you know, this is valuable information to have, because this is showing you, like, if you don't want to do like what they did back in the day, you know, in Africa, you know, they draw those borders arbitrarily, you know, and randomly, and they created all type of problems. So anyway, the more we stick, the more conditional our models are to the nature of the system that we're dealing with, the less fragile it's going to be for failure. This is pictures that we've done with plotting the degree of connections in the US. Again, you can observe, you know, like, yeah, pretty much the picture. And if we go into cities, we can also build these links and observe that people also have very particular collective behaviors in cities. There's downtowns. This is Istanbul, and you can see these links flowing towards downtown. So downtown, it's a very small region, but there, you know, you have the interaction of the whole thing. And you have there the hotspots in which people are mostly meeting and interacting. And I think we did this with credit card data, knowing where people live and where do they go and shop. And this is using Twitter activity, showing where there are the dense meeting areas in the city. And you can see that there's squares, there's downtowns, there's boulevards, there's even, like, you can see like where the metro stations are, and so on. And those are the hotspots, and it's the places where most of interactions are going to happen, and where most of like the exposure is going to take place. And this is using Twitter data, you know, to quantify, just quantifying tweets. I can already like determine these hotspots, you know. So this is information that is sitting there, and it can be very valuable for decision making, and it's just a matter of going after it. And these hotspots, natural human behaviors, again, this is a typical week in cities. You can tell, like, in the morning there is a peak of activity, and in the afternoon there's another peak, and that the peak in the morning, you can tell that it occurs mainly in downtown, and the peaks in the afternoon occur in the peripheries where people live. So what's a natural human behavior, or natural behavior of cities, is to have this contractive and expansive, let's say, dynamic of not only the tweets of individuals, but also, I mean, it's their location, not only their activity, but also because they are moving across the city. And again, it peaks in the downtown that spreads towards the periphery, which means that when we are dealing with a city, you know, I mean, there's times of the day in which everyone it's becoming closer to one another than in other times of the day, and that happens on daily basis. In this paper, we did an analysis of those rhythmic patterns of cities, and I think this is the best slide that shows it. So here you have the radius of gyration of the cities, and you can tell, like, early in the morning that radius of gyration goes down, so it's like a circle in the minimum, and in the afternoon it spreads out and shows a larger behavior. And this pulsing behavior occurs because there's economic activities, because people work, because there's work shifts, because of, you know, the normal urban life that people in the dwellers during the day, like they go to their office places and so on. And that happened because of a reason, because, you know, like, people synchronize their activities such that they can interact, such that they can do business, and so on. And all these patterns are getting, like, increasingly disrupted. I haven't redone any of this for the current crisis, but you can imagine that all of these patterns are getting increasingly disrupted, and it's very important to understand how is this going to affect. So here I have from a paper that I see also in Nature, the effects of social proximity and the spread of behaviors. So social distancing, it helps to reduce the spread. You know, it's obvious, like, because it's limiting the exposure, it's limiting the times in which people are exposing is limiting the effects of super spreaders, is limiting the effect of super spreader events, which is anyone can be a super spreader if you go to an airport, you know. You don't have to be, you know, Will Smith, you know, half of Miami in order to become a super spreader if you visit one of these highly visited places. Anyway, so in the background and in the modeling realm, and this is from Barabas' book, what happens is that what's thought of the structure of social networks, which is this random homogeneous network of random connections, as networks become scale-free, as networks increase the heterogeneity of their connections, the fraction that it's needed to start an epidemic, which is called this lambda number, is reduced that theoretically down to 0 in the limit. So what it means is that the more hops you have, the easier it is to ignite and to an epidemic and to let it run. So the more complex, the easier it is and the harder it is to stop it, pretty much. And events is very important to understand those events, because events like festivals and concerts, you can see the time series, they behave as if they were like natural events, you know, like things that shock the system and makes everybody move towards one particular location, or a huge amount of people move towards one particular location, and increase, and for 1 second stop that were completely disconnected, for a minute connect at all, and with all the consequences. And those random connections, they might seem random, you know, but that's another lesson from social networks, which is the explosive growth. Things that, you know, they seem that you are adding random connections, but once you are sort of in a given limit in which parts are connected already, but they are disconnected from one another, it takes only a few links to make everything connected and for a giant component to emerge, and for, you know, a huge shock or a huge thing to happen. You know what I mean? Just like that, which is like when complexity happens, that people say like, well, where did that came from? You know what I mean? Where did that come from? And it's like, well, you know, because it's been creating itself for a while. It's like they say, the fire doesn't happen because of the match. The fire happens because the grass is dry and ready to burn. So if you have a dry, it's a matter, a dry grass, it's a matter of time until, you know, someone that sparks a match, and by accident, whatever, it's a matter of like human error, you know what I mean, can happen if things are ready to ignite. And so in the last part of my talk, I want to present a paper that we've done, modeling interdependencies and modeling their effects in systems. So in a very abstract way, we represented people or agents they're actually economic agents. They are businesses that we're representing here in a very simple way, just in space, and the capacity to build economic interdependencies in the form of supply chains or this sort of thing, increasingly with one given dimension that we call density. So we can have denser networks in which everyone is able to trade, not with everyone, but with large proportions of the system, and others in which like people are very disconnected to one another. We also analyzed another venue of self-organization, like centralization, like systems in which you have absolutely no centralization, and in the other extreme, perfectly centralized structures, and whatever you can have in the middle. And in these types of networks, this type of layouts or topologies in which you have increasingly denser amount of interdependencies, or increasingly centralized and hierarchical amount of interdependencies, we analyze the spread of failure to understand how the structure, what's the interplay between the structure of the system, a hypothetical structure created by these mathematical models, and its response or its resilience or its fragility to failure. So we choose with a given probability of failure, we choose nodes, and we make these nodes fail, and therefore cascade those failures onto one level or to two levels. And then the question is, what happens if I choose this node to fail, or what happens if I choose the one there, the green one there in the middle, right? How does that spreads or across the system? And the answer here is that by measuring the effects of failure as a one probability that we said collapse, which the collapse probability pretty much is what happens if the behavior of the network decreases down to the point that it's the same thing or dependencies. So we define collapse as the case of going all the way down in terms of the type of, as I said, there were economic products, so the economic agents, the type of production that these agents could have before they fail. And if we let some nodes fail, we measure the probability for the whole system to decrease down to the level that there is no network in the first place. And then we can use knobs to increase the density of the network and to increase the centralization of the network and observe how the system changes its behavior. And in short, what we learned is that there is a very sharp transition between disconnected to densely connected networks, or to decentralized to highly centralized, in which the probability for absolute failure, such that the errors spread across the whole system, they start very robust, but there is a little threshold in which the whole thing behaves as if it's fully connected. And this is important to understand. Why? Because the airplanes matter, because globalization matters, because the way that they have integrated markets across the whole world and within our own economies matter. They are too much, they are too interdependent. And by increasing interdependencies, having no short circuit breaks, and having no, not thinking of like how things are combined together, we create a fragile systems in which we are living in that something triggers another thing and triggers another thing. And I don't know what the solution is like, you know what I mean? Like, it's a very complex problem, but we do need to understand way more the complex behaviors of social systems, both from data and from theory and from modeling. So this is the full picture of this thing. We apply this model to data. So these are real supply chain networks, and we find the same sigmoidal functions. And well, they provide pretty much a profile of how these supply chains look like. And the challenges are huge, man. Like, we have the whole world in front of us, you know, it's a huge village. Everything is connected, everything is interdependent, very dynamic. There's many challenges that we need to go after. And with that, I'm gonna skip these parts and just give few things about social complexity to conclude. So patterns emerge from local interactions. What we do in the local interactions matter a lot, especially when we are like affecting the whole. Links and interdependencies, you know, they must be created spontaneously. You cannot dictate things. You cannot dictate behaviors in complex systems. You can create effective environmental conditions for solutions to be created bottom up, such that they match the complexity of every locality and so on. And there's just like layers and layers and layers of discussion here. But the answer, I mean, and the take-home message is that we need to understand way more the nature of society and the nature of our systems. And now it's the time. We have the tools and we have the opportunity as we never had before with so much data and computation. Anyway, so that's my contact information for anyone who's interested in any of this material. And thank you very much again.
Thank you so much, Dr. Morales. It's very entertaining talk. It shows so many pictures about these complex social network issues. Now the floor is open to questions. If you have any questions, you can either type or or raise your hand. Okay. I have one question. Maybe I can start asking. You show the complex networks and one slide about the friendship is the boys, girls, and a couple other things, and also you mentioned the unpredictable about the social networks. My area is completely different from this, but sometimes I also try to use a network analysis. One thing puzzles me is we can build a network, maybe not as complex as you showed, but the key question to me is how one factors affect the other factors, or how do I know the causal link between those factors, and whether the hub is the causal factors, or whether the one node far away from the hub is the causal factors. I'm wondering if like you showed the case from the collapse slides, those studies, if that can somehow figure out the causal relations between those dots and nodes?
Yeah, so it's a very good question, and there are the different. I mean, what comes to my mind is there are these different types of causality, right? And you have like A causes B, but it could be that another thing is causing A and causing B at the same time. And when we're dealing with complexity, in which you have things that are affecting things and affecting things and affecting things in such weak ways, because it's not apparent, it's not obvious. It can be a third or a fourth order event. It gets really difficult and really complicated to make those sort of inferences. And the first lesson is that it is difficult to make, and therefore whomever is presenting something as if it weren't, you know what I mean, and just throwing a link there, you have to be suspicious or skeptical because of the complexity of these things. They limit a lot the type of analysis that people can do. Another thing, and this is from complexity regarding causality, is that sometimes it's not A plus B that causes C. Regardless, I mean, sometimes yes, A plus B causes C, and we know that we have A, we mix it with B, and you know what I mean, it causes C. But sometimes there's something called homeostasis, which is systems creating the environment that they need in order to exist. So it's like you eat because you are hungry, but you also you live, so you eat such that you can be hungry. You know what I mean? You eat such that you can live. And so it's like what's causing what, you know? And in this discussion, yes, mechanistically, A plus B causes C, but in a relational layer, is really C the outcome that is creating the occurrence of A plus B such that the whole thing exists. You understand? So it's the same, like I eat because I want to live. It's the result that it's calling for the products to be combined together, and because it's what it needs in order to exist. And with this, this is Robert Rosen who talks about this, and it's very, very, very interesting, because he says when we're trying to understand social behaviors and the emergent orders of social systems through the mechanisms that are creating those macroscopic structures, without stepping back and understanding the role that the macroscopic structure has in the behavior of the people, which can be just the maintaining the social order, what's feeding back and really creating the behavior of the people that creates the social order. So I don't know if I throw too many lines there, but yeah, I mean, it is difficult, and but you need framing in order to ask those questions. And that's what complexity provides, framing, so you can understand and put things into boxes.
It's very interesting, very cool ideas. Yeah, any questions? Go ahead. Yeah, okay.
I might have one. Oh, sorry. Hi, so thank you so much for the presentation. It was really interesting. I have one question about a lot of the charts that you showed, you were pulling data from, for instance, like Twitter or phone records, which are, that are kind of objective, direct things that you can observe. But when you're drawing social relational data from like surveys, and it's about possibly a sensitive issue that people might not want to disclose their connection, even in an anonymous kind of an anonymous or confidential way. I'm doing research into the networks between local humanitarian actors in an area that has significant conflict. And so I'm anticipating that there's gonna be people who don't want to disclose, even confidentially, what their connections are in that sense. So what are the tools to maybe frame or mitigate or show the shape of something when you think that people are not going to be upfront about who they're connected to and why?
Right. So it's a matter, the issue arises on the task, what are you using the data for, right? So if you're looking at the individual, right, then you have all sorts of concerns, because you have the individual. Some people agree and they don't care. Some people are very sensitive with this. And in terms of Twitter, there is the possibility to turn yourself off or on if you want, like, these APIs to gather the tweets that you are publishing. The thing is that most of the people leave it on because the nature of the social network is to be open and to interact, right, with other people. However, there's more. The information that we are after, which is at the group level, at the massive scale level, like we're talking about the whole country, it's information that, as you aggregate it, you dilute that individual information. So you stop looking at what a person is doing, and you see more like how region A is interacting with region B, or how region, like, whatever. And by that, what people provide really is one pixel. It's just like one, pixel of what that big picture looks like. But what you work with and what you are able to do analysis, and where you actually are going to get information is from the aggregate level. So for me, I compare it with the census. Like, I don't want to disclose, like, people don't want to disclose the personal information like the census, but the census provides aggregate level information of neighborhoods and cities, such that you can, like, build all these sort of visualizations. And not only it's a coincidence. It's a coincidence that both preserves privacy, but also the important information about the social system is in the societal, is in the aggregate level, because the individual is too heterogeneous. You will overwhelm yourself with data points that seem absolutely disconnected from one another and with very little structure. But that structure arises as you start to aggregate the information, whether in maps or distributions or networks, and so on.
Great. Is there any other questions?
May I ask a question?
Sure.
Hi, Alfredo. I'm a master student in the NAS program in Nutrition Epic Data Science program, and I saw your presentation about there is a super interesting dynamic map showing like different times and how the people cluster in different parts of the city. So I think that's super important and super interesting, especially in the in the period of the COVID. I have a question is, I saw that Google is presenting like a Google Community Mobility Report showing like their difference and changes between different parts of the cities during different days of the week. So do you think dynamic map can play a similar role in like visualizing people's densities or like public densities and surveillance COVID-19?
What's your question again? Sorry, because I didn't understand.
Yeah. Sorry about my expression. So my question is, do you think like people dynamic map can play a role in their COVID surveillance?
Yeah, I think there's even the fragmentation that we did with the US. That is something that I covered the last time that I was there at talks. It's something that people, the people there at the New England Complex System Institute are pursuing, creating, like, taking this into consideration for reopening different places, and recommending, like, okay, what sort of progressive you know, what areas should be taken into account, a relocation, and so on. But in the research realm, I don't know in the practical, I mean, world, if there's something going on already. But it would definitely help, because there you can see, once you understand, again, it's the difference between the map and the territory. So if you have a picture of the map which says like, well, you have that neighborhood and you have this neighborhood, but the reality is that, you know, these two neighborhoods are super combined together, and they behave like a single thing. If I split them, you know what I mean, arbitrarily, I could disrupt unnecessarily areas. So that's the whole idea of understanding how the social tissue of a system looks like. So you can like disrupt the list.
Thank you.
Okay, so we have one. Okay, but it is about the time. I mean, I see some other people also said they have a question. Maybe Ellen Marie. See. Okay, so sorry for that, because the time. You can ask a question. You know, for during the session, the Q&A session is about like in another 15 minutes. You can log in the session. If you don't have the login, you can email Ellen Marie or Corinne to ask the Zoom link. You will have plenty of chance to ask more questions. Again, thank you so much, Dr. Morales, for the very entertaining talk. I'm looking forward to talk to you in the future. Very nice. And you know, it's about the time we have to say goodbye. And for some students, they have a class and to go. So, okay, thank you so much. But don't forget to log in back in 15 minutes.
Sure, thank you very much. Thank you, everyone. Great to talk, great invitation, good to see you all. Bye.
Ellen Marie, are you still on?
Yep, I'm here.
Okay, I just wanted to give you an idea what happened. So there was a small issue, I think, with the embed code for the Friedman stream. So Annie Devane's working on that. We're going to actually do some troubleshooting on that Friday. So we're going to set up a Zoom call and see if we can get the site back up and running correctly. We were able to put a very quick button on the Friedman site, which redirected them to the YouTube page. So people were still able to see it. So it wasn't too much of a hindrance. It's just, I think the Innovation Summit last week, maybe a few things might have been changed in the code.
I see.
And I don't think they would change back. And that's more on the web developer back end. It's nothing that I really deal with on my end. But regardless, we should have that fixed by hopefully, you know, by next session.
Yeah, that sounds good. I'm glad at least there's a hint of what's going on there.
Yep. And then if you want to get me this as soon as possible, I'll try to expedite it for people so that they have it over the weekend.
Thank you. I will do. Should
Okay.
have it this afternoon.
Great. Thank you.
Thanks.
Thank you, Ellen Marie and Corinne.
No problem.
Yeah. Oh, Ellen Marie. Yeah. Thank you. Oh, okay.